Well, good evening, everybody. My name is Mohammed Rawani. I'm the chair of the aerospace chapter of the Environment Station of IEEE. And this is one of our monthly meetings. That we hold. Want to welcome everybody first of the year as well as online. And our talk tonight is called Amazing Radars. And Paul is going to be our speaker tonight. And from what I've read, it should be not only educational but also fun. And it promises not to show any equations more than what we learned in high school algebra, which is fine with me. Every month when I open the IEEE Systems magazine, which is mostly radar articles, I see those horrendous equations, so I don't need them. So here I have to learn something about radar. And we also have to talk about the microwave, the electric in the microwave. It reminds me of my first interaction with the microwave like 40 years ago. I was working at Hidden in Hills, and I would take lunch from home. And one day I had a sandwich wrapped in aluminum foil. And I put it in the microwave oven outside the cafeteria, and I saw all these sparks coming out. So I figured there must be some electric field going on. And lo and behold, I had to wait 40 years to learn now what are the electric fields in the oven. So, video talk about and also issues like radars for air-to-air missiles, which should be fun. Just as a way of introducing about start talking about his background. He received his bachelor's degree in 1960. Right?
Pardon me for interrupting.
From Rensselaer Polytechnic in New York, near Rochester, where I used to go to school. And then he got his PhD from the University of Michigan in 1970. In between, he worked for the Army in various locations and various capacities. And then after PhD, he joined the Hughes Aircraft, and he was doing research there for 23 years, I believe, and retired. And then he established his consulting company. And he's been very active in IEEE. He's a fellow of IEEE and a life fellow also. So he has all the credentials to give this talk. So I stop talking and I give the floor to Bob. And I guess it worked from here. And our expert system is here. Victor, if there is any issue, you will tell.
Is it working on Zoom?
Yeah, I had to mute my iPad because it was causing some sound issues, but I think it's working much better.
Okay, we'll go. All right, good evening. My name is Bob Eisenhart, and I have the privilege to talk to you tonight about antennas. I spent more than 50 years working with microwaves and especially with antennas. The discussion will be very basic with relevant information relating to radiation, the product of antennas. Most of the time will only involve simple antennas. However, I will have a short section with respect to antenna arrays at the end. So let's get started. All right, so I'm zapping you. Does anybody feel that? All right, well, you're being radiated. But you're being radiated by everybody's cell phone in this room as well. and you're being radiated by all the electronics in the building. Okay, that's just the result of currents flowing in electrical wires and pipes and things like that. All right, we're totally inundated by radiation. Well, what's different about antennas is that we create radiation on purpose with antennas. The other ones are not done on purpose. Okay. This slide shows a few antenna types, which I'll discuss at some point. But the question is, what do we use antennas for? We use them primarily for communication. And that implies that there's at least two antennas in any system. One's a transmitter and one's a receiver. Of these showing up here, only the microwave oven is not transmitting and receiving. The broadcast tower only transmits. The other antennas there are used for both transmitting and receiving. The thing that's so amazing about antennas is that the transmitter and the receiver that we're talking about don't have to be connected together. Like in a radio system or a telephone, or rather than as a radio, a telephone or telegraph, they were always connected together by a wire, no matter how far apart they were. But with antennas now, there's no connection between the two, so they can be put anywhere. And as they are today, you can have one on Earth and another one communicating with a satellite millions of miles off in space. So the basics here, let's say, what is an antenna? Well, an antenna is a device that transforms electrical energy into electromagnetic energy. Now, that's a big fancy word, but basically it means radiation. To describe this effect, think of a metal rod that has some current on it, and then radiation comes away from that just because of the current. An antenna also works in the reverse direction. Just as important, antennas are sensitive to radiation. So if we have an antenna and we have radiation coming into that antenna, it will create current on that antenna. So it's a complete cycle. You can have it as a transmitter or a receiver to have a system like that. Now let's make a simple antenna. We can just start out with a two-wire line. It goes from some sort of source of energy, the signal, up to some sort of a load that's insignificant here. But we take these two wires and we bend them like this. And now the current that was flowing on those wires is all flowing in the same direction. So that's accumulating and create quite a bit of radiation now. Previously in the two wires, the currents was flowing in opposite directions that tended to cancel out. So there wasn't that much radiation when the wires are close together. Here, now we're creating a lot of energy, radiation energy. Now current implies the motion of electrical charges. All right, now they can't flow indefinitely in one direction. And it turns out that an antenna is actually a resonant device, just like elements in music instruments, like a string in a guitar or a piano or a violin. The length of the string determines what the frequency is for the vibration of that string. The same thing is true in an antenna. You want to change the frequency of a string in music, you change the length of it. And that's what we do with an antenna. If we have to adapt from one frequency to another, we set the length of the antenna based on that. Let's talk a little bit about, well, all right, I just missed a few clicks here, but that becomes what's called a dipole with the two sides to it. Sort of There's two basic antennas, a dipole and a monopole, and everything else is built out of one of those two. Nothing more complicated than that. But we'll show different antennas that have different radiation patterns. Okay, so we get an oscillation back and forth on this resonant dipole. And we have to determine what the length is, and that's based on what frequency we're going to be using. So I want to first define a few terms with respect to radiation, because radiation and antennas go hand in hand. Okay. Now, radiation is an oscillating electric wave through space at a frequency where it has an oscillation rate based on whatever the frequency is. Just as an example, the frequency in your home, of the power lines in your home, are oscillating at 60 cycles a second. Typically, in communications like this, they're operating at millions of cycles per second, tens of millions of cycles. I'll show you some examples of that. And that establishes the wavelength. And this, with this wave, the wavelength, as you can read it here, is determined by how fast something's going, the wave, which is going at the speed of light. And within one time and one period there, that's how you define a wavelength. And with respect to an antenna, typically a resonant antenna is going to be based on a half of a wavelength. So one of those dipoles that I was showing you before would be a half a wavelength long. So that's how size gets related to frequency, and frequency is related to the application that you're actually using it for. Now, this is all done within the electromagnetic spectrum. And we see it's from 0 to infinity here. All these different types of things are all operating with the same electromagnetic spectrum that I'm talking about with antennas. Now, one thing that's particularly interesting here is the one section where you have visible light here right in the middle. It's just electromagnetic. All this light is electromagnetic radiation. We just don't think of it that way. And our eyes are sensitive to that electromagnetic radiation. So we see light, okay? Now the area that I'll be focusing on is just the lower end of this, where we've got all these bands of frequencies that we're pretty much familiar with just in normal life. AM, FM, radio, TV, cell phones, and on up to radar. And you see then in the next line, the frequency would go from 1 megahertz, that's 1,000,000 cycles per second, on up to 10,000 megahertz for radar. And the wavelength is inverse related to the wavelength, or to the wavelength and the frequency are inverse related. So for the 1 megahertz here, that antenna would be, well, that's a wavelength, so a half wavelength would be 150 meters long, typically. And there are lots of antennas that size, but we're not usually using those frequencies. But you see, as you go on up here to the radar, and that's in an area where I was working, this higher end stuff, the wavelength is down to 1 inch. So we could actually building parts of antennas that are on the order of half wavelength. Now, there's another characteristic of radiation that's particularly important that most people don't have any idea about at all, and that's polarization. So I want to talk a little bit about that. All right, so if we consider two antennas that are in a system, the one on the left, we'll call it the transmitter, a dipole there, and then a receiver over on the right-hand side. So that's just what I'm arbitrarily set up. These two are in the same orientation. So I'm going to use a couple sticks here just to show. If we call that one horizontal and the other one over here is horizontal, that's gonna be the best connection of the radiation between the two. All right, that if and that's called copolarization, when they're in the same plane. It doesn't mean it has to be horizontal. They could be both vertical or like this or anything else, but they should be in the same plane. When one of the two, either one, it doesn't matter, gets cross-polarized to the first one, then your connection between the two, the transmission level is gonna go down. Okay, and that's important. And cross-polarization always ends up hurting. Now, as far as, okay, this chart shows with the copolarization, which is at 0 degrees, where the two things are at the same plane, there's no additional loss between the two. It's whatever it is based on length and things like that. But as the angle, wait, I don't want to do, sorry. As the angle changes and goes out to 90 degrees, you get this worst case, and the transmission loss goes way, way down. Okay, so you don't want that to happen. So what I put at the bottom is when you have a problem with your cell phone and you're having a problem getting good reception, a good thing to do is rotate it around, because it may be that you just cross-polarized with the cell tower. I don't know what the cell tower is particularly, because I don't know what the polarization inside the cell phone is. But I know that you can change it and get different levels of signal through it, so it's worth dealing with. You know, I do that myself all the time. But there is a way around this, and it's called circular polarization. So what happens here is if we take one of the two antennas in the system, whether it's transmitter or receiver, back and forth, it doesn't matter, but you design an array with two different polarizations in the array and the other one, then no matter what this orientation is, it's always going to have some connection with one of these two in the array. Okay, now the loss in this factor is a half of your power level, but it's all the time regardless of what this angle is. Okay, so that's very easy to give up a half of the power level, but never have to worry about the orientation. This is a picture of radiation coming off of a cross-polarized or circularly polarized antenna underneath it, coming up into the sky. And that type of polarization is used all the time for vehicles and aircraft and things, where they're always changing their position with respect to connecting to satellites in the sky. So that's very, very commonly used. I doubt whether it's used in a cell phone though, because it takes more antenna space and it starts taking up more 3D space in there as well. So how do we see radiation? Well, here we have a picture of a flashlight with a energy coming out, light energy, which is electromagnetic energy, although we can see it. It's coming out into a particular volume. And that's what we're particularly interested in. If I change it a little bit, I can change the type of shape of that radiation. And when it gets narrow like that, that's when they're more likely to call it a beam. Well, I take a flashlight like this, okay, and it's got, this is the broad kind of thing, and I can change it by focusing it down like that. You see how much more concentrated it is. The same amount of power that was in this broad beam is now all focused in one spot. And I'm only doing that for one purpose, and that's to define the term we use called gain in an antenna. The gain is what the concentration level is at the peak point of the beam that you're trying to create relative to if it was like a candle in a room where it's radiating out around in a full spherical shape. The same amount of energy put into a concentration, that would be the gain. So I will have examples where I talk about the gain of this antenna is 15 or 200 or whatever. So I just wanted to have an idea of where that term's used. Antenna design is all about controlling the radiation patterns. You have a need to have radiation in a particular direction, whether it's a broad radiation or very narrow pointing radiation. Like when you use dishes, you create very narrow beams and you can get from building to building in a downtown area or something to a spacecraft. Now here, I want to describe the technique that we use in simulators to get an idea of what the radiation looks like. It's called a polar pattern. And polar because it's a three-dimensional pattern that shows the amount of power in this radiating beam. Okay, it's this picture here. In this case, it looks like a tire around a dipole, a horizontal dipole. So that's where the radiation is coming out normal to the dipole. It's not along the lines of the dipole. There's no energy going along the lines of the dipole. And it's very strong out perpendicular to it, and it has some width to it. And you see as it gets, the different colors show the strength level as it gets down into the little holes. Well, I should back up on this description. This red circle represents a horizontal plane that I'm cutting through this polar pattern. And then we can see on a two-dimensional plot, the figure 8 patterns over here are showing what the gain is all along that horizontal cut through that pattern. And if I look in this way around, it's like a tire, you would immediately see that that relates to the blue line over on the horizontal pattern. It shows that it's equal, omnidirectional all the way around. It radiates equal amount all the way around it. So let's take this very simple dipole. This is what was developed back in the days to prove that radiation was really beginning to be understood, was a dipole. So here I have a simple dipole, and I have the radiation pattern below it that I've already talked about, but I want to add one other thing about it. Is that I have what's called a front to back ratio of 1:1. That means if I had energy radiating out of that dipole, it would have amount going in that direction and amount coming in this direction based on this figure 8 pattern in both directions. But I don't want that because I want an antenna that only shoots it in one direction. So this type of antenna, oops, wrong one. There we go. You can put a couple metal rods in proper spacing and placing with respect to the dipole. You don't have to do anything more to the dipole, but it will create a new radiation pattern. As I see there in the front to back ratio now is 10:1. So that's pretty good, and that might be good enough for whatever you want done with this. You can put more of these rods on and increase it up to 30:1. So now you know that you're not getting anything from the back if you're listening. It's got to be coming from the direction where you got the thing aimed. And you can run it on up to 100:1 in the ratio because of the way the pattern is going to be. So these are very common type antennas, particularly for TV reception before we all had cable. Okay, people had Yagi antennas like this on top of their houses aimed at the transmitter, the TV transmitter. Here's an example of just a 3-element Yagi, which in many cases is good enough. And it has a little rotator up here. So if the guy that's using this antenna wants to move it from looking over here to looking over here, or listening to somebody somewhere else in the world and the signal is coming in from here, he can rotate the antenna around. That's very common. Here's a little higher set design. It's going to have a little more directivity, as I showed in the patterns previously. This is a circularly polarized Yagi. It's also called a helical antenna. You can see it's basically the same thing with the helix. And then we have, this one's a little more interesting, and you'll probably notice this. I'm supposed to stand over here, sorry. I've still seen this on houses today that probably don't have cable. This really has 3 different antennas right up there all together. And the frequencies in the 3 different antennas are far enough apart, so they're really not interfering with one another. If you can see way down in the bottom right-hand side, that's actually a bunch of little teeny elements for a Yagi antenna. Okay, and then right in there is another Yagi antenna of a little higher frequency that's above the whole set. And then we have one other type. This is a different type of antenna. This is called a log periodic. And the log periodic is a totally different design from a Yagi. It has a bunch of different length elements in it, and all of these are connected in parallel, so that gives you a very broad frequency band of operation. The Yagi itself has only got one resonant element in it. That's the feed element, and it's a very narrow band. But a log periodic is a very broadband antenna.
Paul,
Question.
in this cases like this, are we talking about the constructive and destructive interference between subsequent antennas? Such that
No.
the radiation is,
No, putting these 3 antennas all up on the same pole, they were all pretty much acting independently. Because the frequencies are so different. Look at the difference in the size between the blue antenna, the red antenna, and the green antenna. And remember, these are resonant length arms. So it's like 3 different tones.
And they don't cross talk to each other.
No, these aren't going to interfere with one another. They may in a very slight way, but not as a big deal. Like I said, I still see houses with multiple antennas on top of them that people never took down, even though they may have cable now.
I have a question.
Question.
Well, the 2 pictures on the right, they have, it looks like extra stuff. Extra.
Okay, I'll address that. On the, let's go back to the single Yagi here. The middle element is the active element that's like a dipole. The element in front of it is called a director. And that's the shorter of the 2 that I added. And the one behind it is called a reflector. And that's the longer of the 2 that were added. So when I had just the 3 elements, it tends to move the beam in one direction. Okay. You add more directors, which is more directors, and they also added more reflectors in the back. So this has really been a lot of effort put into that to improve the pattern. But it still does the same thing. It's got one active arm here, which is the dipole, and the rest of it is all just metal put in there to help shape a beam. In fact, I can comment on that. As I said before, the dipole and the monopole are the 2 basic elements. Everything else has to do in antenna design of putting metal around these 2 active elements to shape the beam in one way or another. This is just another way of doing it. Okay. So I'm going to shift over here to the more common way of actually feeding an antenna is with a monopole antenna. It's just essentially half of the dipole. The other half of the dipole, being a resonant element, is put in there by putting some sort of a ground plane around it. Now, the ground plane doesn't always have to be a flat piece of metal. It can also be like a car, which is very common. So the ground plane is tied into the metal shield of the coaxial cable. So this is a very common, it's mostly often called a whip antenna, which we see very often. Here we see 4 different whip antennas on a police car. Okay. There are 4 monopole antennas, and they're using the police car as the ground side of the resonance. Below, we have a larger whip antenna, which would just be for a lower frequency in a cross-country type vehicle. Over here, we have 2 antennas, 2 whip antennas, one on each side of the car. And if you take any one of those antennas by itself, you would get a omnidirectional pattern from that antenna. But if you put a second antenna in there with the proper spacing, the 2 of them together will create a pattern that aims up and down behind the car and in front of the car on the road. So you gain quite a bit in the directionality of your pattern. The last type of antenna here is something everybody's had and played with. It's just a little old radio with the whip antenna on it. You can change the length of the antenna to vary the frequency that you want to receive, and you can vary the angle of the antenna to get a better polarization. Now, you don't have to know what's going on. You just do it to get the best reception, right? But that's what you're doing. You're playing with polarization and you're playing with resonant frequency. Okay. These are a couple, of course, lower frequency. So we get larger and larger and larger towers, and the towers can become part of the antenna itself. For those broadcast type towers, this is the kind of power that you, pattern that you would get from it. It's a nice omnidirectional pattern. It gives you full radiation around 360 degrees, typical radio or television type orientation. This is another type of monopole where you've changed the shape of the antenna portion on the upper part, put it into the shape of a disc, excuse me, in the shape of a cone, and then the ground part below, you can change the radius of that and the position of that, and what you can get is a slightly varied pattern coming out of it as an omnidirectional pattern. Here's a couple examples of them for different frequencies. A very low frequency over here. This is a very large conical wire setup, and then an inverted one with the ground at the top and the cone portion lower down. This is a very common antenna used today. This is the patch antenna that's used on little GPS things and watches and things like that. The size of the antenna here is about a square inch or less, okay? And basically it's being fed up through a piece of dielectric, like a monopole, and then that's just a big flat piece of metal on the end of the dipole, on the end of the monopole. The dipole, the dielectric here is of a higher value such that it makes the resonant frequency higher for a smaller space. Okay. Now we're to something everybody's interested in, iPhone. These are patterns that I created in simulation, and I was never able to figure out any particularly unique pattern coming out of an iPhone. And I think that's pretty reasonable, because there's so much different stuff going on in an iPhone, and it's a lot more important than the pattern. They always figure, well, you can find a way to get the pattern to connect to the cell tower, but it's more important to have a camera in there and a battery in there and the electronics and all that other sort of stuff. So, the bottom line here is, when you're using a cell phone, if it's not got the best reception, move it, tilt it, rotate it, whatever. Sometimes even it may be behind you where the tower is over here. You could be in between the cell phone and the cell tower. Another type of antenna is a horn antenna. This has a monopole speed down in, like I said, that's the basic antenna right in there. The rest of this is all metal. It's been put around it to contain the radiation that's coming off the monopole, and having it so it all comes out this effective aperture here, and then radiate out to the side here. A simple way to understand how you get the gain of this, if we were to turn this vertically and have it in rain, the bigger the antenna, the more rain it would collect. Well, that's the same thing as an antenna. The gain is higher, more powerful, the bigger the antenna is. And that's just something I say down here. The bigger the opening is. But the horn antenna is very useful, and I'll show you where we use that all the time. All right, let me just go back to that a minute. I wanted to also show how this is dependent upon frequency. So that's what these next curves are. So if we look at, these are curves from that same horn that I just showed. And we have 3 different frequencies here, 8, 10, and 12. And as you go up in frequency, the gain increases. So this is improvement here. And the other thing is, the gain goes up, the beam width narrows down a little bit, because you've got to keep the same amount of power in the beam. Okay. And that's just a simple equation. The gain is proportional to the active area and the frequency squared. It's just, these are the kinds of things you really need to remember when you're dealing with antennas, so that when you're testing something in a simulation, if the gain's not going up when it's supposed to be going down, you're doing something wrong. You don't figure out what it is.
The
Question.
simulation would you be changing the length of the monopole antenna within the horn for these different frequencies?
If you wanted a little bit different frequency, you might tune that a little bit with the monopole in there. But that would be typically, you'd select waveguide for that frequency that you're really interested in. Make sure your frequency's within the band of the waveguide. Then you could tune it a little bit. All right, as you want to get more gain out of an antenna, which lots of people want to do, the way to do it is not make a horrendously big horn, but stay with a reasonably small horn, something about the size of my hands here, and put a dish behind it. So what you do is you radiate out this horn, a pattern into the dish. And the design here is to get the horn pattern just to feed the dish, not be bigger than the dish, because then you waste a lot of energy spilling around the edge of the dish. If you make it too narrow and high gain, then you'll only hit the middle part of the dish and you won't be using the whole dish. So there is an optimum spread on the size of the feed horn relative to the size of the reflector. Now, this is the most common one. It's got to be in the world. It's on practically every house, 18-inch dish. Now, in this particular picture, I noticed that it looks like it has two feeds up here rather than just a single horn feed. And the dish itself is just acting as a reflector. There's nothing magic about it. As long as you're somewhere near the focal point, you can get a good reflection off of that dish. So you can put two horns there and have two completely independent systems working. In fact, I've seen this where there would be three horns close together like that. You got three different channels to three different satellites up in the sky. Okay. Now, your house isn't gonna move, hopefully, and the satellite's not moving. These are geostationary. So once you put this in place, you don't have to move it. Now, the next system, here's a 50-foot dish. To be able to look wherever you want to look, you've got to be able to rotate it 360 degrees around. And you also need to tilt it back and forth like that. That becomes very expensive. And then even more so when you get something like this, 100 feet space dish. Now on here, it's easy to see the rotating circular track at the bottom that this whole system can move around. And there's also a circular arc in here where the thing can rotate back and forth to plus or minus, I don't know how much, but maybe up to 90 degrees. So you could see anywhere in half space. Now, if this isn't big enough, and you don't want to keep making dishes bigger because you want to move them around, you go ahead and add a bunch of dishes together. This is the very large array in New Mexico, where all of these dishes are aimed exactly at the space at the same point, and the energy that comes into all of these is put all together, accumulated, and that's the power that they're getting out of that. Okay. Now, if that's not big enough, then you can go to the Arecibo telescope in Puerto Rico that unfortunately doesn't work anymore because it did work for 50 years. And they got a lot of really good data from it. But one of these cables broke and this thing comes crashing down into the dish, destroyed the feeds and also the dish. But you can see at the time, they could move this feed back and forth on this element. And then it had a circular thing right in here where you could rotate it around. So there was actually a cone in space that you could reflect off of that dish in. So they had quite a bit of capability to look around. You can see the gain here with a 1,000-foot dish is 400,000 times what you would have from a single antenna. Said I'd get back to this slide. I'll talk a little bit more about the repeater tower. I hadn't said anything about that. I did talk about how the antennas are reciprocal. It can be used both as a receiver and a transmitter. And that's what you would put on a tower like this. Somewhere you want to go around buildings or over mountains or any way that you can't shoot line of sight. You have to go from here to here and then over and, you know, go around like that. You put these repeater towers and the only thing you do is you put an amplifier between the receive antenna and the transmit antenna. So it boosts the signal up a little bit. Okay. The one other thing is the microwave oven here. Basically, that's got a big power source, a magnetron in there that has a monopole antenna into a waveguide and dumps all this power into a big cavity. And that's what I'm going to look at here. You can see that from the colors, they're indicating the radiation intensity. The red being the really generate a lot of heat, and the blue, no heat at all. That's what you get in a microwave oven. So to get some sort of even cooking, you have to use something like a platter. And of course that rotates around and averages the temperature of the food as it moves. Now I put an arrow there showing the middle of the platter because the middle of the platter doesn't move. You don't want to put your food in the middle of the platter. You know, most people do. They put their cup of coffee in the middle of the platter. That's the worst place to put it. You want to put it somewhere out towards the edge, and you get a much more even heating from it. All right, now I want to talk a little bit about arrays. You see what the benefits are. They're pretty obvious. What you can't do with a single antenna, you can do with multiple antennas, all the way down to the cost. The cost is now in feeding all the different elements. Anytime you're doing an array, you obviously have multiple elements. And you have to feed each one of these elements independently, both in magnitude and phase, depending on what you're trying to do with it. This is what most antenna people are doing today is working with arrays. Okay. Now I'm going to talk a little bit of using this 6-element array as an example. These are all being fed equally, both in magnitude and phase. So the result is going to be a broadside beam that's going to come out perpendicular to the surface of the array. Okay, so you don't have to know anything about antennas. It's just, say we got 6 antennas there. That's all I'm trying to imply. But with them in this particular position, that you're going to get a beam that's perpendicular to the length of the array, and it's also going to be a fan type pattern. And going across the array, you're going to follow this red line because the array is only 1 element wide. So it's going to be a very smooth pattern. Going down the length of the array, you've got the interference between the different elements. So you get the side lobes, which you see in the blue line. And those 2 lines here track following these arcs around the polar pattern of the array there. And that's just saying the obvious, I guess. This is a different kind of antenna, standing wave slot array. This was used in most of the fighter aircraft back in the 80s that were being built by Hughes. Very unique. This is a waveguide. It's just a piece of rectangular metal hollow that you put energy in one end. And as the energy flows down there, it leaks out through these slots that are shown. And the slots are put in different positions that control how much energy is getting out the slot, and also what the phase is of the energy that's getting out that slot. So you can control all sorts of patterns by using this sort of thing. But what's great about it is you can add all these things together, and I'll show you an example. Now my point here is that with the arrays, in that time, that was an F-15 fighter, you had the array face, which was out in front. It had to be controlled with a gimbal. And it had this array face had a gain of about 4,000, but it also had a beam that's about 2.5 degrees in width. So if you're looking out into space, how do you know where to look? You can look anywhere, but how do you know where to look? Okay. You have to be able to move it in the gimbal, and you normally do scanning of the sky to try to spot something. That can take a long time. And you'll see in a minute the benefit of electronic scanning. This is what that array face looks like in an F-18. Okay, there's 684 elements in there. Each one of those slots has a specific phase and magnitude coming out of it to give a very unique shape to this beam that's coming off of the array. Now I've put 2 lines on this array. I added those on there to show that the array feed structure behind it is actually set up such that you can receive energy and either the top half and the bottom half, or the right half and the left half independently. And what that allows you to do using a system called monopulse finding, direction finding, with this array is what you can spot things in space and zero in on them really quickly. I can talk about that a little bit more when we're done, if we got a little time. But I took it out because it took too much to say directly. Now, this will show us how we can do scanning. Scanning is being able to move the beam of the array without moving the array itself. Okay, so I'm going back to the same 6 elements, and I just have some of the parameters of the elements there. And what we need to know is what the delta phase is, what phasing you're going to put between the elements. Okay, so here's the one equation that's in this presentation. It can be solved very simply from that once you understand the geometry. But the point is that there's a delta phase you see down here, and the E1 is one port, and the E1 phase is the second port, and the delta phase is the difference between the 2 ports. And we have to know what that is. And with this equation, for a scan angle of 30 degrees, if that's where I want the beam to be looking, we set a delta phase of 116 degrees between these 2 elements, between these 2, between these 2. In other words, they accumulate all the way along there. Okay. Now, I haven't brought up the term phase before, and I know that's got a lot of definitions, but with respect to this stuff, it only really means one thing. And that's the difference between 2 different waves, okay? So we call that first wave up there is our reference wave. That might be the number 1 wave on one of the elements. And then this particular wave I'm showing here has a 90-degree phase shift with respect to that. So it has a delta phase of 90 degrees. And that, whatever that shift is, you would shift it within the electronics feeding the elements. It's only relevant in arrays because it has to be relative to something, a reference, and it's a single element. You don't have to worry about that. So here's a single element, doesn't matter what the phase is. This is 180-degree radiation off of that. Now, if I put the same 6 elements and just made a little parallel plate kind of radiation situation with the 6 sources with them 116 degrees apart, and then put the scan pattern down at the bottom, you can see that this is scanned out, and right at 30 degrees, that's where the beam is. It turns out this is a 14-degree beam, but that's not related to the phase. That's related to the overall spacing and the elements themselves. And then the rest of the energy that's all up here, you got 6 times the amount of energy because you got 6 times the number of antennas, and then you've got energy in side lobes and things like that. But that's how you get to change the position of the beam. So now we're talking something that's really massive. Although this is still a very small antenna, and you can think of it relative to the aircraft that had 684 or something like that electronically scanned. Well, that wasn't electronically scanned, but they are now, and we'll see that in a minute. This is an 8x8 antenna. This is something that I worked on for the company. This was back about 10 years ago. This is the main beam here, the gain of about 200. And we wanted this whole system to be able to scan out to 45 degrees in any direction. In fact, have a cone of space out to 45 degrees that you could place this beam in. Okay. This is the result of the design looking in one particular direction. And we see that we just did 4 plots showing at 15-degree steps. out up to 45 degrees. And what's good about that is that nothing else popped way up somewhere and destroyed this nice pattern that we have.
What was the application for this, case rig?
Well, I'll show you in just a minute. There's your answer to your question. Okay, these are the aircraft, F-16, F-18, all the way up to F-15. And these are fully electronically scanned arrays. This shows you what you can do with it. You don't, no gimbals, no moving parts. You don't have, you're not looking at this guy over here and then take a half a second to get your beam over here. You can move within milliseconds. And you can be looking at 14 different targets essentially simultaneously, because it's so fast you can jump back and forth and you can keep track of all these different targets. Of course, you're not seeing them all simultaneously, but in effect you are. You're looking at this guy and then you're looking at this one and the difference. And then you can also attack using, you can control 6 different missiles coming off of your plane going after 6 of those targets just with one antenna. And all of that phase and electronic information is kept in big files. So anyway, that's a key thing, so. Now, in summary, I'd like to tell you what I believe is the most amazing aspect about antennas. Only 160 years ago, a scientist named James Clerk Maxwell came up with a bunch of equations on radiation. And then it took 20 years for anybody to actually establish that he was right or wrong and prove that he was right. And then in only 9 years after that, Marconi came up with a radio. And today, I can take this cell phone and talk with just about anybody in the world because of what Maxwell did. In 160 years, not a long time. So, thank you very much. And I'll. Questions?
The question is, what are practical challenges when you're designing this antenna, let's say for satellites, for radar, for communication? What are the obstacles when you start to design for those different applications?
The biggest issue that's really, that's hard to work on.
What did she say?
Okay, all right. She asked, what are the issues of complex antenna designs today? You know, and this, like I said, is very, very low level. I never even talked about what the impedance, what it looks like looking into the antennas. That's where the real effort is, because as you're looking over frequency or having wide frequency bands, the impedance starts moving. And when the impedance moves, you don't get effective energy into the antenna. They have to be matched up, okay? And that's for single antennas. As soon as you start doing arrays, like these electronically scanned arrays, as you pull multiple antennas close together, they interfere with one another. It's called mutual coupling, and that's very complicated. And prior to computers, that was just totally limiting. What guys could do was a few laboratory experiments that kind of gave them a feeling for what was going on, but could never do any of this stuff that's done today. It's all done with the computers. Question?
Dumb rudimentary question. Can you go to slide 35 for a second?
Think so. Let me see. Supposed to be over there, you know. Oh, this isn't working.
He said, Harold, can you-
It didn't let me use my computer. I could do that on my computer.
That's
Okay,
like,
is that the one?
Is this? We used to use, at least in the 2D space, Smith plots. Is this a 3D version of a split Smith plot?
No, nothing at
For
all.
radiation? Or for directionality for between a cardioid and omni with just a z-axis? Or no, this is not a Smith chart. It's
No.
not plotting radiation.
Not plotting impedance. This is radiation. Not impedance.
Oh, not impedance, so
Impedance is.
we don't know the amount of RF energy.
Well, if part of the design of this is to have it matched over that whole stand. Everything that you do is still well matched at each scanning angle at any direction. That's all part of the contract, so to speak, is to have it with a good match. But this is just the main beam and all the side lobes around it. Okay?
So
This is this is just a broadside pattern. Okay? Now, if we cut down through one of the X or Y planes, and then we look at this pattern, this is what that pattern looks like with the main beam as we scan it in steps of 15 degrees, just to show that it can be done without destroying the rest of the field. So this is all pattern. I haven't ever.
there's no spurs or any other kinds of
Nothing,
unintended harmonics or anything like that.
right,
That's pure waveform.
yes, in the pattern, in the beam,
Got it.
that's correct. And as soon as you if we try to stand that up to 60 degrees, I know over on this side, this stuff would be coming way up here and all sorts of funny stuff going on. All of that has to do with the spacing of the elements. That was all looked into the very beginning. This pattern took 5 years to develop. Okay, and the first thing you look at is the size of the elements and how close together they are. And you put them close enough together so that you don't get any of these other funny spurs. But then you've increased the amount of mutual coupling. And then the rest of the 5 years was dealing with mutual coupling. Okay. Question?
Do you think there's room for improvement with AI and like future improvements on antennas?
Well, I suppose there are, although
Or indicators?
I don't, if AI is simply something that looks at all of the literature that's ever been put out there and comes up with the best way to do it based on that literature, the answer would be no, because these are all things that have been created, new ideas that have done this in the simulation software. The simulation software, we've been doing stuff that you would call AI for the last 20, 30 years, actually, which is, I forget the term, but anyway, you let the computer go through iterations to find out, you give it a range of what you can let the parameters do, and you tell it just go, and it might run overnight. And then it'll come up and leave you with the best one of all those parameters that you worked with. That's kind of like AI, but you're building it into the machine. Question?
I have a silly question. You mentioned rotating nine components over two. I remember Steve Jobs, when he was still alive, he said that if you want a better signal, hold your phone to it. It's almost sort of good. Was that interference? Is that?
No. You
Basic same kind of idea.
Well, you have to both get the stronger part of the phone radiation pattern looking at the cell. And you have to get the polarization correct. Both of those things you can optimize by moving it around and just, you know.
I've seen another moving his hand, like, or-
Sure, sure. The hand doesn't really get in the way. No, I mean, it doesn't, it's not an issue. Any other question?
Yeah, I never understood how circular polarization worked, or you did it really. Finally, it made sense, but I've heard that there's, I don't know if this is right. Clockwise and counterclockwise.
Yes, two different modes, totally independent
But how do they do that with just? two?
by the way they phase the two.
Oh, okay,
Normally, you have two dipoles and one of them is 90 degrees in front of the other one. And that will create, let's say, for example, right-hand circularization. If you put it 90 degrees behind the other one, then it'll be circular polarization.
and with
That would
those,
be left-hand.
those act on your receiver and you're receiving. You're sending out clockwise and you receive clockwise, you get the signal,
Right.
but.
If you don't, it's just like cross polarized. If you're not working on right hand, then they won't connect,
Okay,
okay? But one of them connecting to a linear polarization will connect in any orientation, but you lose half your power. Okay, if they're both circulating in the same way, then you don't lose any power. But with like one of these 18-inch dishes with one little circular horn up there, most of them probably have circular polarization in it coming from the satellite. That can actually be receiving two different channels. Because one channel could be right circular and one channel could be left circular. And they'd both be independent because when you have a circulator, you have, excuse me. There's an element in that takes the circular polarization and turns it into linear. You put it behind the front, the horn of the antenna. You put it in there. And if it's right circular, it'll come through and it'll say end up linear at a 45-degree angle like this. If it's left circular, it'll come through and it'll end up 90 degrees perpendicular to that. So they're really two different modes, just like vertical polarization and horizontal, two different modes. Question?
All insects have a pair of antennas. All insects have a pair of antennas. So human body doesn't act as an antenna, the weak antenna, is it? Have you heard anything? Because when I was a child, approaching an AM or FM radio, the reception, it would improve.
Well, I've only heard some cases where some insects have antennas. They're usually very, very high frequencies because they're very tiny, right? But I haven't really looked into that. I don't know
You don't,
the importance of that, no. Now, there's one thing that I didn't get into here, and that, again, because I think it would have taken too long, is some indifference antennas. I don't think I. Wait a minute. How do I can? Oh, this doesn't move. Okay, no, I can't do it. If you had that little 6-element array that I had, if all 6 elements are all excited at the same power level and the same phase, they all work together as one antenna, and you're gonna get one main beam out here, and then some little side lobes to it. But what if I take of the 3 on the left-hand side, have those at a plus power level, and this is at a minus power, in other words, 180-degree phase shift. Well, what do you think you're gonna get right on the axis? You're gonna get 0, because these two are exactly the same, only one's a plus and one's a minus. So you're gonna get a null right on axis. And what you get is rather than one big null, or one big beam, you get two beams like that with a real sharp null in between. And this type of antenna, using two antennas together out of phase with one another, creates a null on axis. And this is the type of thing that if I were gonna go find a cougar or something around here that's got a neck collar on it, and I wanna go around and find one, I would use a 2-element antenna and set it up so that when you got it spotted, the signal drops out. And that's very sharp and very precise. If you got a broad pattern, it would just kind of get louder and louder and a little bit softer. You wouldn't know exactly where it is, but you go with two antennas, you get a difference pattern. You get a sharp null and it goes get louder and louder, and then it goes zip to nothing. And then come back up again, and you would know very precisely your angle. But a difference pattern is part of the monopole system that I was going to talk about with the fighter arrays, where I showed they use 4 different sections. All right, if you took the top half as one antenna, and the bottom half is another antenna, and looked at them with this difference pattern between the two, you would get a pattern that had a lobe above the horizon and below where, well, we'll just say where you're looking as a horizon. Okay, you get a pattern above it and you get a pattern below it. And so if you got a signal on one of those and not the other one, you would know that your target is above where you're looking or below where you're looking. So that's information, all right, a lot better than having one big beam out there that it's out there somewhere, okay? Then you look at the vertical line and you take the right-hand side, the left-hand side, and do that also as a plus and minus receive. So you'll have 2 lobes with a null in the middle, and you'll hear that you'll see a receive that's coming from the right-hand side now, and before you saw it from the top side, you combine that 2 information, and now you know your target is in the right-hand quadrant, upper right-hand quadrant. So all you do is start turning your target to that upper right-hand quadrant, and you'll just bring that target right down to your axis. And if you're shooting a missile at them, your missile's gonna hit them. And you get information on every pulse, and you're sending out radar pulses, thousands of them a second. So you're getting this information back very quickly. So you're using this monopulse, they call it monopulse, because in one pulse, you get directional information. Now, it only tells you what quadrant something's in, but that's a lot of information relative to no information. Because it tells you, just turn a little bit in that direction. The next pulse will tell you again, next pulse will tell you again, and you just zero right in on it. Okay? That was developed during Second World War, but it was never used in the Second World War because they didn't figure out how to get it into any application at that time. It was still after the war that they started using. Then all the fighters use those now, and missiles. How do you think they zero in? They don't just have a radar that shoots one beam out there. They got to figure out where the target is with respect to their beam. And they do it by monopulse. So, another question?
How do they use drones? If they wanted to shoot.
Well, the radars would be the same. It doesn't matter whether the drone is just a way of carrying something. The radars are.
Yeah.
Or if you did it visually with a TV camera, well, that's different. There, you can pick out your targets very easily, like we did with Maverick missiles. Back when they were talking about smart missiles, where you could fly them into a window, okay, after you launched the plane. Well, because the Maverick missile doesn't have a radar in the front of it, it has a TV camera. And you just lock that TV camera right on the window and the guy just steers it in like with a little steering thing. And drones have visual when you see these things on TV and they show you in the news, they show you a picture of something like a building. And they put a cross on it. That's the picture of getting back from a missile that's flying into that building. And then all of a sudden you see it hit it. Okay,
Great question, because of open up little cameras, 5G. Whatever, is there any concern that there's a problem, with radiation problem, so for health and so forth?
I haven't heard of anything. You know, usually the higher generations of cell phones like that, they're doing more with, maybe a little bit with the phone itself, but a lot more with the towers. Okay, so the towers, like you see in my first picture, can you put the first picture up? Right, there was a picture of a cell phone tower in there.
It's not.
Just the introduction. Yeah, this one. Okay, so you see here on the left-hand side, there's a typical cell tower. And it's broken into 3 different sections. And the cell tower radiates with these 3 elements off, and this 120 degrees. So now it's not worrying about 360 degrees, it's only worrying about 120 degrees. So it's 1/3 the number of signals getting involved, okay? And they've got arrays, they're using arrays here that travel in a vertical arrays, which mean they would be very flat patterns. It'd be, the pattern of fusing the 3 arrays together would be a nice pattern that covers 120 degrees. Okay, but it wouldn't be way up and it wouldn't be way down, it would be very flat. So it concentrates the power out around for the area. Okay? And each one of these is probably made up of a whole stack of antennas in there, each one of them. And then you use that as one subarray, or each subarrays, and then they go together and they cover the 120 degree section out in this direction. And you can see same thing for the other 2 120 degree sections around the whole tower.
Thank you.
I have a question. Before we go, you might have some questions from online people, but no, okay, before we do that, I have a question which is related to the first question Shaheen was asking. Let's say I'm using the antenna as the receiver, and all of a sudden I'm bombarded by noise. What are the considerations that I have to have in the design to protect myself from that noise?
Well, noise is very broadband stuff.
Right.
So like when you're driving down in a car and you're driving along listening to the AM radio and all of a sudden you start getting a bunch of static. It's usually coming from something like electrical transmission lines or something like that, power lines. I know there's one place on Valley Circle where I'm driving along there, there's always a lot of static. And then I get a half a block away and then it's not there any longer. So it's some noise that's coming in from the outside. There's not much you can do about that.
Well, in the optical domain, we used to work on agile systems that any noise coming has a spectrum. It's not completely flat, throughout this as a spectrum. So if I can move my transmission or reception into a frequency band outside that, let's say, bell curve shape,
Sure.
then I should be okay. So all I have to do is to have the mechanism inside that moves the frequency to a range or a domain that is outside that
Well,
spectrum
yeah,
of
if you can get away from the noise, do it.
Yeah.
But usually the noise is not a single frequency particularly,
Yeah.
unless it's some device that's near you. And everything that we build has a radiation requirement on it to limit the radiation from it. Okay, so like there's radiation limitations on microwave ovens. And even on refrigerators, anything else that's electrical, there's a radiation limit built into it. So obviously, if you can get away from it, but if the noise is there, the noise is generally pretty wide.
Okay, if no other questions and there's no online question,
I think,
No, okay.
there was a comment about how clear the presentation was, but
I appreciate it.
Yeah.
Is there anybody on the Zoom?
Let's-
Yeah.
let's thank our speaker one more time. I'm Georgie. And by the way, next month, Bob will be giving another talk. I believe it would be August 27th, the third Thursday.